Hello everyone, my name is Margarita Khokhlova, and today I'm going to present you the paper entitled Learning Embeddings Across Time Geographic Areas Represented as Graphs, co-authored by Nathalie Abadie, Valerie, Gouet-Brunet, and Liming Chen from IGN, France, and Centrale of Lyon, also France. So first of all, I'm going to quickly present the project and scope of which this work was realized. And the project is a European project Allegoria, which stands for Advanced Linking and Exploitation of Digitized Geographic Ethnographic Heritage. And in this project, lots of archived data of mostly representing different pictures of France, starting from 1920s and ending up in around 80s, were digitized. And now these vast collections should be explored, and different tools for the researchers in order to basically research and retrieve and find some correspondence and somehow to organize all this data should be created. Now I'm coming closer to this work, and this work actually deals with aerial images, and we are approaching a question of aerial image matching, addressing it from a new side. So first of all, in all the data which I was talking about, they're really of various nature. So there are aerial and ground images. There could be some different text and descriptions. We also dispose old and modern maps. And usually, if we want to match or to find a given object in computer vision, nowadays we use a visual representation, and we try to match the visual features of such an image to all the other images and find the ones which correspond. Here, in this case, we are targeting aerial images, and we want to try to use not the appearance information, but the relative information between the objects. So in this image, for example, you can see there's an aerial image on which the annotations of human-made objects are superimposed. And in green, you can see the buildings which were there like in 2004, and being there, it's like a modern picture. And you can see that there were many changes in the landscape, mainly due to the man-made changes, which makes it maybe not that easy to actually really say whether this landscape, well, basically, if you want to match this area in green with the modern one in pink, it's a question how easy will it be to match this data. And this work is actually answered this question, or propose one of the answers. Some more on the inspiration. So what we are looking for, what was the inspiration by this work and intuition? If you have different data, well, for example, here you have just even some annotated data, and then you can represent this data as fully connected graphs. And then these graphs, well, for the graphs, we already have many methods to try to match them and to use them and to describe them. So what we want to do, we want to pass from an aerial image to some kind of an annotated map, and then to try to match those, and not the images themselves, where the changes can be really drastic, even due to the season or weather changes. And we hope that the graph which contains the relative information can be a bit more robust, and we can use it to match the data. Before passing to the approach, I will quickly talk about the data which we're using in this work. And we're using the topographical database from IGN across 4 dates, 2004, 2010, 2014, and 2019. To say we try to match near identical regions across these dates. And more precisely, we use Dataset, which is actually a manually annotated data, manually annotated aerial images taken across all these years. Now about the pipeline of the method itself. So what we do, we create the graphs from vector data representing, for example, a aerial image which we want to match. Then we create graphs of an area, and we try to, by representing them as descriptors, passing by a graph convolutional network, we want to basically give in a query, for example, of 2004, we want to ideally return the same graph of the same area or near identical area from 2019. So how do we select the areas? Well, the areas we selected for this experiment, we use the following algorithm. We just decided that we will find the points of interest, which would be different historical monuments, churches, administrative buildings, and all that. So this data are available in the Dataset. And we will take the area around this object, about 200 by 200 square meters. We will just take all the geometrical objects inside this area. And here we can see some examples. While creating the dataset, we noticed that some of the points of interest were located really close to each other, so some areas were overlapping. And in this case, we consider this as the same area, same unique area on the map. Sorry, it's not unique, so it's just the same area on the map. Now about the graph formation. So the moment we have our geometrical objects, we create the graphs in the following way. So each object, geometrical object itself, would be the graph node, and we cut the objects like roads and rivers on the junctions. And the links of our graph are obtained using ternary triangulation. So we use a triangulation in order to create a fully connected graph for the distinct dates. Once again, here an example. So overall, our graph would be then representing an area of 200 by 200 meters with all the geometrical objects located in it, and they have attributes, 2 geometrical attributes, such as a normalized perimeter of a geometrical object and electricity, like this length divided by this of the bounding box object. And we also use a node nature, such as whether it's a road, river, building, and other types of an object. And finally, here A would be the connectivity matrix, which just establishes whether the 2 nodes are connected or not. So it is matrix of connections. And using that, we created a database for our tests, which contains basically 3 French regions with graphs coming from 4 distinct dates. And we also added 1 more region located in different. So all these regions are located in the east of France, and this is the region from the west of France. And it's added without correspondence, just as a noise data. And we have a resulting database of about 12,000 graphs. About the evaluation, well, we use map average precision. That is to say that the query graph for a given year, for the query graph, we will retrieve all the results in the database, and then we'll just find whether the real ground truth for this zone was there or not, and at what and which place it was returned. And first of all, the baseline. So before proposing a new method, we actually just decided to use a Facebook's asimilarity search baseline in order to retrieve the graphs. across the dates, and we got quite good results, as you can see. So we got about yes, and the results, the accuracy is decreasing when the gap between the research and data query and database is increasing, which is logical. However, in this case, we are dealing with ideal conditions because the data are manually labeled, and we know that they're pretty accurate. So the geometrical attributes across the years match pretty nicely. So we decided to go to a more realistic scenario, and we tried to add some noise to our attributes with a different amount of noise. So 0.001, 0.1, and 0.01. And we noted that if we're adding noise to our attributes, then the map average precision is decreasing really drastically and dramatically. So even with not such a big amount of noise, we have already the performance which is decreasing significantly. So phase method is very nice, it works really fast, but it is not robust to noise. That's why we search for an alternative. And this is the alternative that we came up with. Well, we propose to use a CMS-like graph convolutional neural network, in the heart of which we use the graph convolutional net from Keep and Welling. However, we decided to use it first as in the CMS approach, and second, in the original work, they use the created descriptors for each of the node of a graph. We, however, are interested in a single descriptor representing the graph and our area hence. So instead of training the descriptors for each node, we actually use the max pooling and the fully connected layer to obtain a graph-wise descriptor. And we train it pretty simply. So we use positive pairs. These are graphs corresponding to the same area across time, and negative pairs, it's a random areas graphs across time, so which don't correspond to the same area. And we try to increase, well, to make the positive pairs more similar and the negative pairs less similar. So a standard CMS-like approach. We also evaluated two main pipelines in this scenario. So we tried first to learn on the same regions across time, and then testing the retrieval also on the same regions, but from a different time frame. For example, we can train on 2019 and 2010, and then retrieve from 2004 and 2014, for example. And the other one is more general, that we try to train across time and then test on a completely different unseen region. And here are the results which we obtained. So we used different, for example, and the first one is cross-time learning and inferring. So we can see they obtain the results which are less high and less good than the phase research. However, even if we're adding 0.01 noise with a standard duration of 0.01, our method is still pretty robust to noise. We're still getting, well, taking into account that we have a unique correspondence, almost in 50% we have the corresponding zone returned in the top 5 database returns, which was not the case for the Facebook search. Then the second experiment, when we use 2 departments for learning and 1 for testing, and we use the data for the biggest gap between them. So that is to say the year 2019 and 2004. And we trained the algorithm this way on 2 regions and tested on the third left region, so which was never seen during the training. And this is the results. However, pay attention that if before we're using all the regions for training it for testing, here it's really just 1 region in the database and in the query. So these numbers are in reality, if you'll use all the regions, it will be a bit lower. Just we tested the trained on some, so we had to use less for the test. Okay, so now I'm going to conclude on this method. So this paper actually proposes a brave new idea. So we want to approach the vertical image research and retrieval from a completely new side by passing via semantic information and using a connected graph as a representation. The proposed method is robust to noise, and we can find a unique zone correspondence in more or less 50% of cases, even on that same data. And what's even more interesting in this approach, there are lots of cross-domain possibilities yet to explore in graph search, because we can easily add, in this work, we limited ourselves to purely geometrical information by imagining a real scenario when there is like an aerial picture, and we might be able to segment it using a neural network. There are lots of methods which show that it works pretty nice. However, and that's why we don't use any labels but geometrical ones. However, if you will have more labels, for example, if you'll have some annotations, postcards, you'll have some information about the region, it's always very easy to add a node to the graph, and to this information can really affect significantly, help significantly the search of the correspondence. So there are many different options which can be still explored to improve this work, and we consider this as a first break in this direction. Well, thank you very much for your attention. Please, if you have any questions, don't hesitate to contact us. If you want to play with a dataset, it is available here, and also our GCN CMS network is available here on this link. Thank you very much.